Okay, I'm gonna solve a sample static equilibrium problem like number 1265 on the homework due Thursday night. Okay, so this is a pretty typical static equilibrium problem, and there are two things that you need to um, think about during the whole problem. So in static equilibrium, what you know is, first of all, that the acceleration of the system is zero. So the sum of the forces is zero, or the net force is zero. And in the second one, there's no angular acceleration. So what that tells you is that the sum of the torques are equal to zero, or the net torque is equal to zero. So what you need to do is pick a system, draw a force diagram, and then use that force diagram to balance torques and forces. Okay, so I'm just going to redraw this. The system that I'm going to pick is the beam right there. So if I redraw it a little bit bigger, my setup is going to look like this. Got the beam here. Got the person right there, and we have a cable. So in terms of forces, we have a tension force here. And for these, it's actually useful to draw the force at the location that it's acting for the purpose of calculating the torques, because we need to know that radius. The beam, we can treat the weight of it as if it's coming straight from the center of mass. So I'll just label this. This will be 1,450 kilograms times g. That's not 1,450 grams. That's 1,450 times 9.8. The tension here, I'll just call this T, and T max is 15,000 in this problem. Whoa. What is that doing? And then we can draw the components in like this. Or I'll call this Ty, Tx. And then there's going to be a force from the wall here. And if you think about the force on the beam from the wall's going to push out on the wall. So I'll just call this X. I guess it might be like a normal force, but what you classify it as doesn't really matter. And then we have, if I look at this tension force, I think of it, it's kind of trying to rotate this thing counterclockwise. So if it's going to stop that, I'm going to guess here, I think that the wall exerts an upward force on it too, so I'm going to call that Fy. The direction for that isn't important. Your algebra will tell you whether you picked the right direction for it. Okay, so the guy has a mass of 80 kilograms. So we also have this force out here from the guy, and that's going to be 80 times g. Okay, so 1, 2, 3, 4, 5 forces to deal with. And I guess what we'll do is balance the forces first. So let's do this. Sum of the forces is equal to 0, and that's going to be true for both the y direction and the x direction. So we'll say Fy plus Ty. So we did this one, minus 1450g minus 80g. Did this one, did that one. That's got to be equal to 0. And then in the x direction, Fx minus Tx equals 0. Did this one, did that one. So that's all the forces. And we could go ahead and solve here, but I'm going to wait. I'm going to set up the torque equation first. So if we set up this, sum of the torques is equal to 0. What I need to get onto my picture now are the radii that go into our cross product, our cross F. All right, and for that I need to define a pivot. So I'm going to choose this as the pivot point because I don't know what Fx or Fy is, and I'd rather not find out if I don't have to, and I know kind of what all the other forces are going to look like. So this rate, I keep doing that. Hold on. Okay, so this radius vector here, nope, that's not one that we need. Let's try that again. These go right through the pivot, so they're not going to contribute to torque at all. So this one, that's the center of the beam, and the beam is 6 meters long, so this is a distance of 3 meters. The guy is located 2 meters from the end of the beam, so it's a 6-meter beam. That makes this 4 meters, and the tension force is all the way at the end of the beam. So that makes this 6 meters. So the torques that we have to deal with are going to be, remember we're doing R cross F. All of the angles are equal to 90 degrees, so R cross F just becomes R times F. Okay, so I'm going to choose counterclockwise as positive, which is what the book defaults to. And so what I have is the beam would cause a clockwise rotation, so negative 1450 G times the radius of that force, which we decided was at 3 meters, minus the torque from the guy sitting on the beam. So that's minus 80 G times the radius of that guy. He's at 4 meters. And then the tension force, the x component of the tension force goes straight through the pivot back here. So that's going to contribute nothing to torque. It's not going to cause rotation. So we're just going to have the y component of tension. I guess that's where the cross product comes in. But again, because we already broke it into components and are focusing only on the 90-degree angles, then we've kind of already taken care of that cross product. So I'm going to now add that. So Ty times the radius of that force, so that's going to be 6. And let's see, are we missing anything? 1, 2, 3, I think that's them all. So this is going to sum to be equal to 0. So what we can do now is we can actually solve for the required y component of tension. And that's just going to be 1450 plus 80. Hold on. I'm trying to get all fancy here. That's going to be 1450 G times 3 plus 80 G times 4, all divided by 6. And so this is, hang on one second. Okay, so back to where I was. If we calculate Ty now, we get 7,628. 7,628 newtons. And what they started the problem with is that they said that the cable supporting the beam's rated at 15,000 newtons. So if this is 15,000, then Ty max, that's like this side here, and they give us this angle as 30 degrees. So Ty max is going to be equal to 15,000 times the sine of 30. Sine of 30 is a half, so that's going to be 7,500 newtons. And so the question is this, should this guy be worried? Well, the tension required for the torque to balance is greater than the maximum. So short answer, yes, he should be worried. Okay.